This is the video lecture for simple harmonic motion. It follows along in sections 10.2 and 10.4 in your textbook. Alright, so when the spring has no mass hanging on it, its unstrained length is at the top. And then when mass is added, the spring then is pulled downwards. And this now becomes the equilibrium position. And what we can do is we can cause the spring to oscillate back and forth by displacing the spring some amplitude, and it will move back and forth. The amplitude is the distance, or the maximum distance, from the equilibrium. Period is the time it takes to complete one oscillation. So that's a full, complete motion. So starting in the middle, down to the bottom, all the way up back to the top, and then back returning to the middle would be a full motion. And then frequency is how many cycles it completes in 1 second. It's the cycles per second. Period and frequency are related to each other. Once again, period is the time it takes to complete one cycle, whereas frequency is how many cycles an oscillator completes in 1 second. So therefore, period is the inverse of frequency. If we think back, and we haven't done too much work with this, but if you think back to rotational kinetic energy, angular velocity, omega, depends on the 2 pi, because that's 2 times around in a circle, or pi is 180 degrees, 2 pi would be 360 degrees, so that's all the way around in one circle, and the time it takes to complete that circle. The period for a spring, the time it takes to complete one cycle, depends on the mass and the spring constant. For a pendulum, the period depends only on the length of the string for the pendulum and the acceleration due to gravity. We've already said that the period of a pendulum depends on the length of the pendulum, that's the string length, and g, the acceleration due to gravity. The period does not depend on amplitude unless the angle is more than 8 degrees. This is due to the small angle approximation for using sine of some angle theta. We'll not really go into this too much as to why it doesn't work in class, but just to understand that the period of a pendulum really only depends on the length and the acceleration due to gravity. All right, here we have some springs, a little demonstration here. And these are all ideal springs because they'll follow Hooke's law. So as I put some force on there due to the weight, because we're looking here, if you can see that we're on the planet Earth over here. And I then take that weight off, I add on some more weight. The spring here extends a further. Now, I'll take this off and we'll go back to real time, back there. All right. Now here is my spring. I'm going to show the energy of the spring. Here we go. Right here at this point, here this is its unstrained length right here, like that. I add some mass on there. It now has all potential energy. So what I'm going to do is I'm actually going to give it a little bit, and we can see right here at the bottom, we get a little bit of elastic potential energy. So now I'm going to start this here at 1/16th time. As the spring falls, it gains kinetic energy. It also gains elastic energy. And as it goes back, this column here shows the total energy. So as the spring moves back, as this oscillates back and forth around this equilibrium point, the maximum kinetic energy will be right when it's moving at the middle. That's when it's going to be going the fastest. Now, let's add some friction. This is going to produce what we'll talk about in the next video lecture, damped harmonic motion. But if we add some friction here, you see the thermal energy continues to gain as it moves back and forth right here. and slowly the spring will stop moving.
I want you to realize that these results for a pendulum have their restrictions. Small angles, and we discussed quantitatively how small you would like to allow, and also the mass has to be exclusively in here and not in the string. We call that a massless string. To give you some rough idea of what these periods will be, substitute for L 1 meter. And you take for G 9.8, take the square root, and you multiply by 2 pi, and what you find is that the period is about 2 seconds. So, a pendulum, 1 meter long, has a period of about 2 seconds. 1, 2, 3, 4, 5, 6. So to go from here to here is about 1 second. If I make it 4 times shorter, L 4 times shorter, the square root of 4 is 2, then the period is changing. 4 times shorter, the period must be 2 times shorter. We make roughly 25 centimeters. I'm not trying to be very quantitative here. Now the whole period must be about 1 second. 1, 2, 3, 4, 5, 6. So roughly 1 second. So you see that the period is extremely sensitive to the length of the string. I now want to compare with you the results that we have for the spring with the results that we have from the pendulum to give you some further insight. We have the string and we have the pendulum. And I'm only going to look at the period t, which here is 2 pi divided by the square root of m over k, and here is 2 pi times the square root of L over G. If I look here, there is a mass in here. If I look here, it's independent of the mass. Why is there a mass in here? That is very easy to see. If I take a spring and I extend the spring over a certain distance, then there is a certain force that I feel. That force is independent of the mass that I put at the end of the spring. The spring doesn't know what the mass is you're going to put on. All it knows is, I am too long and I want to go back to equilibrium. That force is a fixed force. If I double the mass, that fixed force will give, on double the mass, half the acceleration. If the acceleration goes down, the period of oscillation goes up. It's very clear. So you can immediately see that with a spring, the mass must enter into the period. Now go to the pendulum. If I double the mass of my bob at the end of a pendulum, then the vertical component of the tension will also double. That means this restoring force, which is proportional with the tension, will also double. So now the restoring force doubles, and the mass doubles, the acceleration remains the same, the period remains the same. So you can simply argue that there should be no mass in here, and there isn't. How about this K? If K is high, then a spring is stiff. What does that mean, a stiff spring? It means that if I give it a small extension, that the spring force is huge. If I have a huge spring force, the acceleration on a given mass will be high. If I have a high acceleration, the period will be short. And that's exactly what you see. If K is high, the period will be short. G. Imagine that you have a pendulum in outer space. There's no gravity, nothing. The pendulum will not swing. The period of the pendulum will be infinitely long. Go into the shuttle, where the perceived gravity in their frame of reference, perceived, they're weightless, remember? Their perceived gravity is 0. You take a pendulum in the shuttle and you put it at this angle, you let it go, it will stay there forever and ever and ever. The period is infinitely long. But take a spring in the shuttle and let the spring oscillate, and it does. So you can actually measure the mass of an object using a spring on the shuttle and let it oscillate if you know the spring constant. And that's the way it's actually done. So you see indeed that these things make sense when you think about it in a rational way. We have here in 26100 the mother of all pendulums. It is a pendulum oops. It is a pendulum which is 5.1 meters long, and there is a mass at the end of it which is 15 kilograms. The length is 5.18 meters, and the uncertainty is about 5 centimeters. We can't measure it any better. And the mass at the end of it, which doesn't enter into the period, is about 15 kilograms. The period, which is 2 pi times the square root of L over G, if you substitute in your length of 5.1 meters, you will find 4.57 seconds. 4.5 seconds. Since you have a 1% error in L, you're going to have a 0.5% error in your period, so that is about 0.02 seconds. So this is my prediction. Did you expect anything else? 45.75. One of the most remarkable things I just mentioned to you is that the period of the oscillations is independent of the mass of the object. That would mean if I join the bob and I swing down with the bob, that you should get that same period. Or should you not? I'm asking you a question before we do this awful experiment. Would the period come out to be the same or not? Some of you think it's the same. Have you thought about it? That I'm a little bit taller than this object, and that therefore maybe effectively the length of the string has become a little less. If I sit up like this, and if the length of the string is a little less, the period would be a little shorter. Yeah? Be prepared for that. On the other hand, I'm also well, I'm not quite prepared for it. I will try to hold my body as horizontal as I possibly can in order to be at the same level as the bob. I will start when I come to a halt here. There we go. Now, you count. This hurts. Ah. I want to hear you loud. Oh. Ah. Ah, thank you. Oh. 10T with Walter Lewin. 45.6 plus or minus 0.1 seconds. Physics works, I'm telling you. I'll see you.
Here's a quick sample problem. A spring has an unstretched length of 10 centimeters. A 0.5 kilogram mass is hung from the spring, stretching it to a new equilibrium length of 15 centimeters. The mass is then pulled down so it oscillates. First, I'd like you to calculate the spring constant. Second, tell me what the frequency of oscillation is. And third, what effect will increasing the amplitude have on the frequency? Please explain. Have a good night, and good luck with the problems.